Every linear transformation you apply to a vector space possesses a mathematical reflection. Identifying this reflection reveals how the operator interacts with the geometric structure of the space. To understand this, we operate inside a Hilbert space, a complete vector space equipped with an inner product, named for the mathematician David Hilbert. Look at this standard linear algebra identity. If you take the dot product of a transformed vector, ax, with a second vector, y, you can move the matrix A to the other side of the calculation by taking its transpose. We can upgrade this mechanism for infinite dimensional spaces. We replace the dot product with a general inner product, and the matrix with a bounded linear operator, t. To move t across the comma, we define a new operator, t star, the Hilbert adjoint. The adjoint acts as a bridge. It allows us to move an operator from one side of the inner product to the other, while maintaining a consistent relationship between the vectors in the space. Defining the symbol is only the first step. According to Theorem 3.9-2, we must prove that this adjoint actually exists for every bounded operator and that it is uniquely determined. Start with the inner product of tx and y. Treating y as fixed makes this a bounded linear functional with x as variable. Ries's theorem guarantees a unique vector z, so this equals the inner product of x and z. We define t star on y exactly as this vector z. The existence of the adjoint is an unavoidable geometric consequence of the Ries representation theorem. It is vital to distinguish the adjoint t star from the inverse t inverse. The adjoint exists for all bounded operators, while an inverse requires strict bijectivity. They serve distinct roles in operator theory. The adjoint follows strict rules. Scaling an operator by a complex number alpha makes the adjoint the complex conjugate of alpha times t star. Moving a scalar to the second slot of the inner product requires this complex conjugate. Consider a product of two operators. Applying t, then x to vector x, what is the adjoint when shifted across the comma? We move sequentially. S jumps first, becoming S star, followed by t. The adjoint of st reverses the order to t star s star. This algebra mirrors matrix transposition, reversing order and conjugating scalars, while maintaining validity for infinite dimensional spaces. This equation, the C star norm property, links the norm of the product t star t directly to the square of the operator's own norm. This symmetry is a prerequisite for quantum mechanics. In quantum systems, physical observables, quantities like momentum, are represented by self-adjoint operators, where t equals its own adjoint. Because a self-adjoint operator is its own reflection, the resulting eigenvalues are guaranteed to be real numbers. This ensures that the math predicts values that can actually be measured in a physical laboratory. The Hilbert adjoint t star is a unique operator guaranteed by the Ries theorem. It defines how we move transformations between vectors and provides the primary mechanism for solving operator equations in complex spaces. If this breakdown clarified the role of the adjoint for you, like, subscribe, and share. Let us know in the comments which theorem or functional analysis topic you want to see explained next.